Okay, well, hi everyone. Today we have a really cool talk by Robin. Robin is a PhD student in TU Wien, where he works with Laura Kovacs, and he does a lot of really cool stuff on the vampire theorem prover, and he just knows a lot about SMT solvers in general. Today, though, he's sharing some really cool, interesting new work where he's going to use egraphs for probabilistic reasoning in the context of side channel attacks. And so I'm really excited to see how these two seemingly disjoint topics are going to be connected. So Robin, please take it away.
Thank you for the introduction. Um, so I would like first to introduce myself. I mean, you said already quite a few things, and indeed I am a PhD student of Laura Kovacs, and my interests are indeed SAT, SMT, and automated theorem proving. But just for completeness, because I think nobody knows me here. I'm originally an engineer, so more on the practical aspects and on the mathematics. And also a piece of trivia that's not particularly relevant to the topic, but I also studied Chinese for some reason. But one thing that is actually important is I am not a security expert, nor a term rewriting expert. So this particular research has some open questions, and this is kind of what I would like to share with you here. And if you have some insights or some questions because something is not clear, just jump in and ask right away. Okay, so let's dive into the topic. So in the title, there is this concept called side channel attacks. And I will use an analogy that Roderick Bloom presented at CAV this year. Imagine that it's like 9 p.m. and you're walking home and you see your neighbor's house looks like this. And then the next day, around the same time, it looks like this. Well, you can infer that yesterday they were home and today they are probably not. And this is a side channel attack. Why? Because you can infer something about the presence of your neighbor based on something you observe that has nothing to do with observing the neighbor directly, right? The lights are just a side effect, a side product of your neighbor being there or not. And essentially, hardware chips are a little similar. So if you have a system that encrypts messages, right? So it takes a specific key and then a message outputs an encrypted message. The hardware will behave differently based on what the key is. And in particular, you can measure the power signature of the key and differentiate with a different key. And this we don't want because that means that we're leaking information to a potential attacker. So what we want is a chip that behaves similarly, or at least it's very, very hard to distinguish between two separate keys. Okay? So how do we do this in practice? One thing they do, the security people, is they mask the secret. So say you have 1 bit, okay, because it scales relatively trivially. Then what you do is you split this into n shares, such that only the XOR product gives you the secret back. So why is this useful? Because now, if the attacker does not know S1 or any of those shares, they have no way of inferring S. They don't get any information on S. That makes it harder to get. So for example, let's make a bold assumption that if you have a bit that is 0, it's just 0 watt compares to the baseline. And if it's a 1, then it's 1 more watt than 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 if it's a 0, right? It's a simplification, of course, but the system still makes sense like this. So if you have 1 share, you can measure twice the system, and then you see that you have slightly more power consumption, and then you can infer a 1 or a 0. Now, if you have 2 shares, then what do we get? Well, for a 0, we get 0, 0, or 1, 1. And for a 1, we get 0, 1, or 1, 0. So on average, you get the same power consumption, right? But now if you measure the variance, you can see a difference. And this scales, I mean, this process continues. And the more shares we have, the higher the moment we have to measure. And this is exponentially harder to get the secret. Okay? So what is conceptually what we want. What we want is to prove that for all keys or all secrets, like a pair of them, their power consumption is roughly distributed the same way, or actually exactly distributed the same way, which is hard in practice to model. So as always, we just formalize an attacker and we idealize it. And we say the attacker can, within the circuit, measure T wires. The higher the T, the more powerful the attacker is, and the more sturdy the circuit must be. And based on the values of those T wires, can they infer what the secret is? So this looks like this, right? So for all
Robin, can I
wires,
ask you a question?
yes, of course.
Is this like conceptually a bit related to like hashing, where you're trying to like distribute things across your like memory banks and stuff like that? Because like from a hardware perspective, we just take a bunch of bits and we XOR them together, and that's one way we can like generate the index.
I would say yes. So it's meant to be hard to predict the outcome. So for example, say you have those shares, right? And the first thing you do is you calculate S within your circuit, and then everything become like the entire execution of the circuit becomes now very predictable. But if you don't, like the name of the game is to not do that, such that the circuit behaves differently based on how the shares are distributed. Does that make sense? Okay. So we have this kind of formula which says that if we probe, so if the attacker measures the value of a wire, it must be that we still do not have any correlation with the secret. And with shares, oh, well, first of all, we can ditch one of the quantifiers because this saying for every pair the probability distribution is the same is equivalent to saying that it is independent. And with shares, now, I said previously that if you do not know one of the shares, that's sufficient not to know the secret. And that's exactly this, right? So if any of the shares is uncorrelated with the wire, then we're good. So we want to prove that the circuit always keeps this property. So abstractly, we have the circuit, which is a definition, a bunch of logic gates, which we can express in logic relatively easily. And we want to prove that for all inputs to the circuit, the property holds. This is quite difficult to do. And in practice, this is something that we do very common, is we do refutation instead. So this quantifier complicates everything. And proving that this is true, we don't want to do that. So instead, what we do is we say, does there exist a particular set of inputs, such that the circuit is satisfied, but the property is not? And if that is not the case, if we cannot find such an input, then we have concluded that our circuit is safe. Yes? Okay. And also another side product of this is we get a very nice CNF formula, which is easier to reason over. We like normal forms for efficient reasoning. All right, here is an example of a gate that is non-interferent. So it's an AND gate that takes X, which is split into two shares, and Y, also split into two shares, and outputs Z, that is also split into two shares. Now, one thing that is worth noting is this R. So for two consecutive executions of the circuit, even with the same inputs, we might not want to have the exact same result. And so, I mean, we want Z to still be correct, right? The XOR of those two. But the R is there to jam the signal a little bit, to make it a bit less predictable. And for example, here, if you measure L1, you will get some correlation with X1, which is perfectly fine. But here, this XOR gate will kill the correlation with Y0. So if Y0 is 1 and R is 50-50, 0, 1, that means that S1 is 50-50, 0 or 1. And if Y is 0, it's exactly the same, which means that based on what we measure on S1, we cannot infer anything about Y0. And that will be our running example from now on. Okay, so this formula is a little bit complicated. What do we have there? We have some conjunction, disjunction, so that's Boolean structure. We also have the fact that we probe a certain number of wires, that's pseudo-Boolean. And we have some probabilities, which are equality plus some special functions. All this mess we don't want to deal at the same time. Like this is very complicated. So the SMT approach is to split this into two parts. You have the SAT part, which takes care of the Boolean structure. So which are the things that can be true at the same time such that we don't violate the basic structure of the problem. And then the SAT solver will say, hey, here are the set of equalities that hold. But it does not understand anything about what those equalities mean. And that's what the theories are doing. The theories take a bunch of equalities and say, oh, actually, they are inconsistent. And in case of inconsistency, they will send a conflict clause, which will help the SAT solver refine its search. It's like a teacher, essentially. The SAT solver is very naive. It will just come up with some solution, but does not know any better. Submit it to the teacher, which are the theories, and then the theories will refine by saying, well, actually, you forgot those and those facts, and please refine your model. And if the SAT solver does not find a solution anymore, then we're actually happy because we proved that there are no counterexamples to our property. And if the theories say, okay, well, actually, the model that the SAT solver is giving us is correct, then we have SAT, and this is bad, which means that either our circuit is wrong or our modulization is wrong. Okay, so what does it look like here? So since we did the refutation thing, the quantifiers went away, which is very nice. And we get here, for example, probe. We will abstract this and just say a wire may be probed or not. And that's just true or false. And we don't care what it means. What it means will be handled somewhere else. And this somewhere else will say, well, if the number of if the number of wires the attacker can probe is 3, and we have more than 3 of those that are true, then we have a conflict. And then on the other side, we have the probability statements. And again, we just abstract them away. So the SAT solver will just say, oh, I have some propositional variable. And then the theory will know what it means. So SAT, very well known. We don't need to deal with this anymore. The only thing we have to be careful with is we have to be able to communicate from the theory to the SAT solver conflict clause. So this is kind of what it looks like. So the SAT solver has a simplified version of the problem, which are the lowercase letters. And then the higher case, the uppercase letters, represent what the theory reasoner knows. Okay. So if the SAT solver says A is true, then the theory reasoner will say, okay, A is true. And from what the SAT solver gives the theories, we may infer new things. That might be new equalities, that might be just internal data structures that keep track of the just the thought process of the theories, essentially. And now maybe the theories conclude that we have a conflict. And we have to tell the SAT solver to refine it. But the problem is the conflict is between D prime and B prime, of which the SAT solver is not aware. It does not know what those mean. So we have first to do conflict analysis. What is this? Is basically you go back and you say, why did you think that? Why did you conclude that? And you do this until you reach atomic elements, which a SAT solver may understand. So for example, D prime was implied by D and B prime. So what we do is we say, okay, well, now D must be part of the explanation. This is something that the SAT solver understands, and so this is acceptable. Now we still have B prime, which is still not understood, and we do the exact same. B prime was implied by A and B, therefore, this will be part of the conflict clause. And so this conflict analysis procedure essentially is just keeping track of where things come from, and then go backwards to justify them. Okay, so here is the example that we mentioned earlier, where Z is the output of a XOR gate, where R is uniformly and identically distributed. Okay, so we want to show that the output is independent, so Z is independent of X. And since we're doing by refutation, what we want to find is there a solution such that this does not hold? So this means they are not independent. Let's drill this down a little bit. What do we have? Okay, in blue, we have probability statements. Okay, and then in red, we have equalities. That's fine, that's the easy theory. And then in orange, we have nonlinear real arithmetic. So we have this melting pot of theories that have to coexist together. And okay, let's see how that works. So we have the input, and let's use an egraph approach to things, because this is what we were going to talk about in the end. So as part of our egraph, we have this term, P of ZX, and we can apply some custom rewrite rule, which is the chain rule on P of ZX, which gives us P of Z given X, P of X. Okay. Now we have this term, P of Z given X, and we can apply a new rule, which is the law of total probability. And since we already have this expression, we just expand it into this P of Z given X R, blah, 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 blah. But we also know that R is independent of anything, actually. So P of R given X is going to be 0.5, no matter what X is. P of 1 minus R given X is also 0.5, and P of R is also 0.5. So this node does not virtually exist in the egraph, it's just a representation. And through some arithmetic magic, we end up with concluding that P of Z given X is 0.5. Okay. Well, that is cool because it's a general expression on Z and X, which means that actually P of Z given X is equal to P of Z. So Z is independent with X. We can plug this expression here, and then we get P of Z given X is equal to P of Z times P of X, which contradicts our premise, and we have a conflict. And we're happy, we have proven our objective. Now, there are a few things here. In blue, I have highlighted just rewrite rules on terms. Those are exactly your bread and butter, if I'm not mistaken. And in red is the tricky one, because this one does not come from a term, it comes from an equality. Because we have this special equality, we can conclude another equality, which is a little bit less obvious in the case of egraphs. Okay. Do I need to introduce what egraphs are? I assume that everybody knows what egraphs are.
I think no.
But can I ask? But can I ask
Yes.
that you go back to the previous slide and just
Yes.
say one more time, maybe a little bit slower, the distinction between something coming from a rewrite and something coming from an equality?
Yes. So my understanding of rewrite rules is that you take a term or some representation of it. So in the case of an egraph, it would be not exactly a term per se. And then you can generate a new term that is equal, you put them in the same E-class. And if this term already exists, then you're merging E-classes and you're making progress, correct?
Mm-hmm. Yes.
But in this case, it's not just a term, it's two terms that are equal. Because we know that P of Z given X has some expression that does not depend on X, that means that actually if we had P of Z given not X, we would have the exact same result, which means it's independent. But you cannot just rewrite P of Z given X into P of Z. This is unsound. You need this extra context. Does that make sense?
So can I actually didn't follow quite how you figured out that P of Z given X is equal P of Z.
So you have this, I mean, you can do it two different ways. So P of, like the probabilities are some sort of polynomials, right? And then you end up with a polynomial that does not involve X. So you can conclude that you can get rid of it. The other way to think about it is you can do the exact same reasoning, but on P of Z given not X. And if P of, so the variables are Boolean, right? So if the P of Z given X is equal to P of Z given not X, which are the only two values you can have for X, that means that P of Z is independent of X. Does that make sense?
I'm saying that that is the context that you need. Like somehow you know
Yes.
that P of Z given not X is also 0.5.
Yes, that's one way to write it. But so it's one way to justify it, but it is sufficient to say if I have a general polynomial that expresses this in terms of X, or in terms of the right-hand side argument, and it does not involve X, it means that it's independent.
Okay, yeah, I see. Okay, I see. I think that makes sense now.
Yep.
It's related to like just do a live range analysis on the right-hand side, and you have something that is independent of X, right?
Yes, yes, that would be that, yes.
From a hardware perspective, like it's quite funny that we spend our whole lives trying to remove XOR gates precisely for this reason, because to reduce the amount of power your circuit's consuming, you want to avoid gates that can just generate a load of toggles, basically. So like, unless you're in this specific world, you want to like avoid XORs as much as you can.
Here we want them very much.
But here you like them a lot. It's kind of funny.
Yes, yes. Yes, it is a bit counterintuitive sometimes. Okay, so egraphs, breeze through it very, very fast for just a graphical display, how I represent them. So just the circles are e-nodes, and there are function applications to e-classes that are the squares, and e-classes are just everything that is equal together. So these slides, super easy. Now, why do I think that egraphs are a good idea for that? The first reason is we get a lot of different equal expressions with the rewrite rules on polynomials because we don't really know in which direction to search, which means that we need them to be as compact as possible, right? And egraphs do that. The other thing is SMT solvers already like egraphs. They like, I think every mainstream SMT solver has an egraph in there, which means it's also very well studied for conflict analysis and proof generation. And then efficient congruence closure is also a pretty nice side effect of egraphs. Now, what is hard about this problem is first, well, probability calculus is not very well understood and studied. In particular, I don't know of any calculus that is complete, that we know for sure we can prove everything probability related. I mean, there is Kolmogorov calculus, but it's basically just enumeration, which is not very helpful in our case. The other difficulty is combination of theories, where we have probabilities, we have polynomials. In some ways of writing the problem, we also have Boolean algebra. And all of these have to coexist. And just polynomials are difficult. They are difficult within egraphs, without egraphs. It's a tough challenge. And also, there is this thing, complex term introduction. So if you remember in here, we had this very beautiful small term, P of Z given X, that to find a solution, we just had to expand this in this giant monstrosity. And of course, as a human, my intuition told me, hey, I know that this is everything gonna simplify and it's gonna be nice. But to properly formalize this as rewrite rules, it's not so trivial. And we don't want to apply those rules super eagerly, because otherwise we just produce a lot of garbage that we can never get rid of. Okay, now why are we talking here with the egg community? Well, I think from what I explained earlier, this is relatively straightforward, that I want to saturate. I want to saturate because I do not know in which direction to search, so let's search them all at the same time. And the rewrite rules are also pretty nice. Now, the thing is, the rewrite rules are not super standard, and this I would like to ask you if this is something that egg actually does. But basically, those let's go back there. Those probabilistic statements, they are actually new functions every time. So P of zx, I just write it like this for compactness, but it's actually a different function symbol than P of z given x, naturally. And P of z given x was not part of the original statement, so I introduced new function symbols. Does that make sense?
I think so. Are you saying that it is what you're saying? It doesn't appear in the input, and that is the
Yes.
potentially tricky part.
I
Yeah,
mean,
that's
it's not necessarily tricky, but I don't know if egg does this already.
yeah that is supported.
Okay.
And also the thing that makes termination go out the window, but it's supported.
Okay. Here, everything is fine because there are finitely many function symbols we can introduce, and there are also finitely many expressions, but it's just everything is exponential pretty quickly. Okay. What was I saying? Yes. I do not believe egg does conflict analysis.
That's correct. It does not have conflict analysis.
Yes. And proof production.
It does do
That's
proof production.
Oh, really?
Yes.
Oh, it's surprising because they usually go hand in hand.
Yeah, I mean, I think that this is so proof production. I see Oliver just joined. Was sort of added post facto. The proof production is well considered and thought out, but it is designed for like translation validation mostly.
Mm-hmm.
Like I did, I got from A to B, and I want to see how I did that. One could probably build conflict analysis on top of this, but it also
Probably, yes.
doesn't support backtracking. So why would you build conflict analysis on top of it? Because you sort of need both
Fair
together.
enough. Fair
Yeah.
enough. So for those reasons, I actually am writing my own Frankenstein monster, trying to implement all of these things. It's not great yet, but work in progress.
Great.
And the other thing is the lemma generation that we already talked about, and new term function. So apparently this is not a difference, so this can just go away and this can go away. And proofs are very important, right? Because we're doing the verification of a hardware circuit. And if we just run the solver, and then the solver says, yes, all good, we accept the system. I say, why? Just trust me. That's not very acceptable for proofs, right? I mean, for verification in general. Okay, so here is the first thing that is a non-term rewrite. I mean, a term rewrite neophyte. I hit this wall somewhat recently. Is this nonlinear real arithmetic does not terminate, and this is bad. So you have this x. So if you have the inverse rule, right, and associativity commutativity, then you might generate an infinite number of terms, and this happens right here. If you have two, like this is a XOR gate expressed in probabilities, slightly different formalism than what I used in the beginning of the presentation. But then you get exactly that, and then it never terminates. So it's fine if there is a conflict. It's not fine if there is. So the way this happens, briefly, is if you match the associativity rule, right? So you generate a new node, and you can match it again, and then generate this new node, which is 4, which was not part of the original. And of course, if you can generate 4, then you can generate 6, and then 8, and then blah, blah, blah. So you have this chain of 2 times 2 times 2 times 2 times 2 times x times half times half times, which is not useful at all. And I saw this problem, and it reminded me very much of something that we also have in first order theorem proving. But first, I Googled it quickly, and there are some solutions that I already know, like normal forms where you expand. That's not great because for deep circuits, we actually have plenty of very small polynomials that we would like to be solved locally, and we don't want to expand into exponentially many terms. Another solution is just give it to a Grosvenor basis or CAD solver. We actually have one on our team, Grosvenor basis expert, and she told me don't do this because the polynomials are they just hurt. Double exponential complexity. And they are, from what I understood, this is a worst case complexity, but a most case complexity, let's say. And then the other thing is, okay, we can say, oh, well, then we apply the associativity rule less often, let's say. But it's still only semi-terminating, which we don't want, especially on a finite problem that is definitely decidable. So I said this reminded me of a problem that we have also in first order theorem proving, and exact same thing. If you have this clause for all x is equal to f of xa, then you could, in principle, rewrite f of xa into x here and generate infinite number of those terms, which are not useful. So we have those redundancy criterion, which tells us that a clause is redundant if it is implied by smaller clauses than itself in the clause set. And then if that is the case, we can get rid of it and we don't lose any proofs. And that is super great because then we can filter out all the garbage and only keep relevant clauses. Now this problem is undecidable in first order logic. So we have sufficient conditions. So in particular, this rewrite will not happen because we rewrite a bigger term into a smaller term. So that's why it will not happen in Vampire, for example. But there are other such rules. And I was wondering if it would make sense to have such a thing also in rewrite systems. Say, here, we identify that there is a loop. And if there is a loop, it must be that the overall function application should be unit. And if it's not, we should have a conflict. And then once we have detected this, then we can get rid of it. Does that make sense?
I think I understand part of this. This would be a good time to note that, in fact, many of the people in this chat probably do not know this. There is a relatively new, but I didn't like announce it or anything, feature in Egg that sounds very similar to this. I think it's probably a weaker form, where you can, when e-matching, you can basically abort that match if one of the matched e-classes is the same as the root e-class that you are matching at. It's basically, it doesn't account for all of the cycles that you are that you're considering here, but it does help a lot. And I added this because there was some use case that was suffering, right? And it helped a little bit. So yeah, I mean, I wonder, it made me think of this, and it's especially tempting. This is a very exciting potential solution if you can solve it sort of at e-match time, right? If it's something where you have to post-analyze the graph and do like cycle breaking, that sounds harder. But if it's if you can characterize the cycles as ones that are smaller than the e-matching patterns, then maybe this is very good. The thing that I get worried about is, what about longer cycles? Like, cycles that like you could sort of think about like with identity things, it's the cycle's very short, right? It's like, oh, one times x times one is itself, right? But you could imagine you have like negation gives you like a sort of cycle of like 2, or like maybe you have some goofy operator that's like, quasi negation that takes like a cycle of like 5 to like become itself again, right? These things could lead to similar explosions, but would be harder to solve with the similar technique. But maybe that just doesn't matter.
Oh, that's actually very good. So a Vampire has this exact mechanism. I mean, not this exact mechanism, but this 2-step simplification where we have exactly what you said, where, well, this rewrite will not happen in the first place. because we know trivially that this is pointless. And this is what you explained with when you have a cycle. And I was actually not sure that this is complete still. That was also my first intuition, but I don't really know how to convince myself that you're not losing proofs by doing that. And then on the second round, so when in Vampire you generate new clauses, you will run the clause through subsumption checks, for example, which are much more expensive, but allow you to remove some more redundant things. So you have these 2 rounds where whenever you can infer from the get-go that something is useless, you don't do it. And then after that, you have still a cleaning up period.
I see. Very interesting.
Okay. So now that's one problem solved. Brilliant. Second problem is this lemma introduction that we discussed earlier. And this reminded me a little bit of what SAT solvers do as user propagators. So a user propagator is a lambda function that the SAT solver calls at regular intervals, saying, here are a bunch of literals that I have assigned. Can you tell me more? And the user propagator will say, yes, you can actually propagate more of those things, and I will justify them later. I think for egraphs, it could be possible to do something similar. Probably a little harder because of the explosion of number of terms. If you talk to a SAT solver, you're just talking through literals, and this is a one-on-one mapping, and this is very easy. If you're talking to an egraph, you talk about equalities of terms, and then the egraph abstracts this to e-nodes and e-classes. And then if you want to talk back as equalities, then you, I don't know, like you probably don't want to generate all combination of equality terms within an e-class. So that's something that I was wondering if you had thoughts about. And let me just like explain briefly what the user propagator looks like in a SAT solver. So this is a similar picture as before. The SAT solver has just assigned A. Calls the user propagator says, okay, then A must be true. And then B must be true, so B, and the user propagator says B prime. And then at the end, the user propagator decides that discovers that E is implied, and it just tells the SAT solver, here, there is a new literal you can use. And the thing is, now the SAT solver does not know where this literal comes from. And so we have the exact same mechanism of conflict analysis as we had before. So the SAT solver might ask, hey, where does this E come from? Oh, E comes from D and B prime, which comes from A, B, and D in total. Right? So this is roughly in a nutshell what user propagators do. I would be very curious if you could do the same with egraphs.
I think that there are the skeleton of some mechanisms that could provide the same thing. I think the thing that is making it hard for me to understand it, and maybe others have a better grasp of this, is, well, in egraph land, there's not only the sort of introduction of the literal, which is like you're building a term, but there's also things becoming equal to another thing, right? Like those are sort of the two kinds of assertions, right? You can assert that a term exists, which is interesting already on its own. And you can, of course, assert that some term is equal to another term. The E-class analysis mechanism would be, sort of has enough hooks to do both of these things. It's definitely designed to, so this is a mechanism by which the user can, provide code that reacts to the insertion of new terms or new equivalences. One thing that is, perhaps we should have been doing for much longer, but I think is relatively a new insight for us, is that, of course, there's nothing stopping an E-class analysis from in either of these situations, reacting to something and putting new stuff into the egraph, either creating more terms or creating new equivalences. So in my sort of understanding of your picture here, that's the sort of final step that you said. It's like, oh, the user
Yes.
propagator is seeing big E and then like asserting little e on the SAT side.
Yes.
So I think the mechanisms are all there. Again, the setting
Well,
is different, right? Because
I think there's one big
go ahead.
missing piece though, Max, which is that existing egraph libraries don't give you provenance for why things showed up in the egraph. They only give you equality proofs. So like Z3's egraph and egg and these other egraphs, they just support like why are these two things equal, not why is this fact true. That's something we're trying to fix in egglog. We're going to give you provenance information so that you could really ask why is E in the egraph, and you would get that chain of where it came from. So I think with some tweaks to the proof production of an egraph, you can get something like this. Is my take.
Yeah, and let me just restate a little bit what Oliver said using the vocabulary I was saying. We support proofs for why two terms became equal, but you also need, for this little e, you need a proof of existence, right? Like where did e come from? Even if it's not equivalent to anything yet, you need to justify, who put it there and for what reasons.
Why? Why though? Because the term can
Oliver?
just exist out of oblivion, right? You can just have like, here is a term. Now, how do you prove that this is equal? This is the business of the proof in conflict analysis.
Well, I think the egraph mixes the way that we use egraphs in like egglog and egg often mixes terms and meta level facts, like saying that this term is true. So like if you put a term in there that said assert E, like E is true, that's more of a fact that you've like derived via some of your rules. And the fact that it's in the egraph says that E is true.
I'm sorry. I think we have different terminology for what
Right.
terms are. In first order community, a term is not a Boolean value.
Exactly. Yeah, that's what I'm trying to get across is one way to use egraphs is to not only to store terms, but also to store terms with store like facts about those terms. Like the lower bound of this term is 2. Or this term is true. We've figured that out via some reasoning. And you can use the egraph in that way. It's not really a way that SMT solvers generally use them right now. But like imagine storing the whole like set of clauses you know to be true like in the egraph as these meta terms.
So just a bit of context here. Robin, in this talk, you have been using the sort of terminology of egraphs that are parallel to egg, which is something that we understand. But we've also developed this newer version of the tool called egglog, which is sort of links it up with data log and sort of takes a relational perspective. And one neat thing there is that terms are sort of encoded as rows in a database, just tuples, if you will. And that's nice. That has a lot of benefits. But it also sort of bends your brain a little bit because while I agree with you that on the egraph side, the mere existence of a term should not carry any information, right? Like you're pulling it out of thin air, and that's totally fine. On the database side, of course, the adding of a row to a table is depending on how you interpret that table, could potentially is a meaningful action.
Yeah, basically we started abusing egraphs in this way where things in the egraph have meaning and we think it's a good idea, turns out.
Right.
So you're saying that this database representation of the egraph is not only a representation, it's not just a way or data structure that holds something that looks like this.
It would also hold more facts that you've learned about these terms.
Yeah. Yes, and just to put a fine point on this, I think the confusing part is that, so we all, and this is like a quote unquote good idea. We get good performance from this. We're using tables to represent terms.
Yes, I also
That's
copied this idea in my solver. So
great. But we have the mechanism for tables. And so we're also using tables to represent other things, right? Now the mechanism is very similar. It's all tables under the hood. And of course, for some of those tables, like, one table is asserting, the lower bounds of things, is keeping track of the lower bounds of things. Another table might be keeping track of other pieces of information. Of course, we want the provenance of those facts, right? Because like those are interesting facts.
yes.
And so that sort of, I guess, like begs the question. There are some tables which are merely keeping track of the existence of terms. Like there's a table called add or mul, which is just basically storing the add or mul terms that we know about. Perhaps we are interested in the provenance of those terms as well, because after all, they're just tables. And it's the same mechanisms under the hood that you might use to ask about the provenance of other facts. So I guess like the point I'm trying to make is it is a matter of interpretation, right? You are correct for sure that in the world that you are thinking about, the existence of a term does not and ought not to carry any information. But that's just a choice, right? Like what you want to, the semantics you want to ascribe to the existence of some term in your database may or may not have meaning. And we have to support the fact that it might have meaning. I guess that's all I'm trying to say.
To have one strategy that works for everything. Is that a right way to think about it?
Yes, because we sort of have no choice because we are representing everything as tables. And certainly some of the tables we have to have provenance for.
Right, yes. Okay. So even more justification.
It
Right.
turns out that like the provenance and the equality proofs go hand in hand, and I don't think it's that much more of a burden to have the provenance, but we'll see. We're still implementing.
Okay. Yeah, and so that leads me to kind of the final slides, which is the idea is to try to disentangle this mess of a lot of different things together into 3 different layers. So the stat solver, we talked about it already, and then to have the egraph that just handles equality, and then to have some sort of oracle that is able to communicate efficiently with the egraph. And apparently you said that the machinery is already existing.
I don't know about
correct?
this particular machinery. We're working on provenance proofs for the egraph, so that might help you build something like this.
So the thing is, so there are 2 reasons why I started writing it myself. First is just to learn. And second is because of this conflict analysis thing, which is really important in my case, because if no conflict analysis, then no communication with the stat solver, and then all the propositional structure goes out the window, and this we cannot afford. But if that would be interesting to see if you produce proofs. In general, it's, I think, at least from an SMT or SAT perspective, it's easier to generate, like to have conflict analysis than to generate proofs. I think it is.
I guess I don't see the difference from the egraph perspective. I think you have to get the proof to get the conflict, but
Yes.
maybe I'm confused on that. I think the real thing missing from existing implementations is backtracking. Something maybe on the horizon for Egglog, but we'll see.
Yes, that's what I was going to say. I think the major, while certainly there are lots of, technical things to be sorted out, I think that, in broad stroke, using broad strokes, there are capabilities very similar to a lot of the things that you're talking about for like conflict clause generation or user propagators existent in our community. The big one that is missing is backtracking. And that sort of, is such an important perspective shift that it like colors the rest of the, mechanisms as well. Like conflict generation is sort of less meaningful without backtracking, for example. I think another one is, how should I say this? Like, I think our adoption of this relational perspective in Egglog has been very fruitful in terms of performance. Like, we definitely have state-of-the-art e-matching performance over there. But I think it has further muddied the waters, because now we are sort of adopting a sort of logic programming perspective where we're monotonically building up a database of facts. And I think it has led to a sort of further divergence of what we talk about over there compared to what people using egraphs and SMT solvers mean. Now, there's probably still a lot to exchange there, but it has to go through one more layer of sort of vocabulary and direction.
Also makes it harder to backtrack.
I do think it does make it harder to backtrack, right? Like, as you said, our bread and butter is about instantiating quantifiers. And the reason why we are the best at it is that we build database-like indices. And we keep track of, all these nice indices. And of course, that's just one more thing that we have to backtrack over. And it's probably a very expensive one to backtrack over.
Although, like, I don't know, me and Eli have been talking about backtracking and comparing it to what like Z3's does. And the backtracking is very crazy and complicated with all these pointers in like a traditional implementation. Whereas if it's all in a table and you use timestamps, you just you lop off the table after a timestamp.
Totally.
So there's some benefits too. It's not just
I have
downside.
hope that we can do it, and I suspect that we can, and it can even be done very well, but it hasn't been done yet. And
definitely
having indices makes it one step more complicated.
For sure.
Well, the thing is, once you have merged two e-nodes, or two e-classes rather, then this information you have to keep track of everything that was in there, right? To backtrack, and this is probably expensive and not trivial to maintain.
For sure. Yeah, I think that one of the big insights that I've been thinking about recently, and it sounds like is also very relevant to your talk, is this thinking about how to hook up our understanding of E-class analyses, which we have been, that's what we call them, and we've been using them for program analysis for optimization purposes, with the SMT perspective of user propagators, or even the richer side of modulo theories. So you touched on that a little bit, and I think that's a very interesting, I don't know, connection and line of work that I think there's a lot more to say on.
Okay.
Yeah.
So I just have like the last conclusion slide, but we discussed already a few. So this was like to incentivize discussion, but apparently this was not necessary to ask, which is great. But so that brings us to the conclusion of the talk. And quick summary: I think probabilities are good case study for egraphs, or use case rather, and we have actually discussed some problems that are now, I think, kind of solved. If you're convinced that this cycle elimination procedure does not lose completeness, then I'm also convinced, and that's one problem that is.
I'm not convinced that it doesn't lose completeness.
Okay.
Yeah, I'm actually a little suspicious about this.
No, you should be very suspicious. I'm just saying that this is something that was hacked up and proved useful in at least one circumstance, and could lead to something. Yes.
All right. I mean, worst case, this would miss conflicts, which means that we would end up saying, well, actually, I don't have to go all the way back. Right here. Right here, we would miss some conflicts, and we would answer stat, which they reject the model of their verification, and at least it would still be sound. So even if this is not complete, it's still fine, I guess.
Right.
It's very hard to have
Right.
completeness with egraphs because you have to very carefully analyze your rules. I'm not really sure how to do it.
Well, it's undecidable, right?
Yeah, but like maybe there's some rule sets where it's decidable. I don't know.
Yes. All right. Thank you for your attention and your help.
Yes. Okay. Thank you.